Today I'm going to finish up chapter 14 and cover chapter 15. And 15 is relatively short, so we should be able to finish. And then if we have time, I can answer some questions about project checkpoint. So this is where we left off last time. So we're talking about file system implementation. And one of the issues has to do with if there's anything inconsistent with the file system, then some recovery is needed. So where does inconsistency come from? So real quick, because the file system has its data stored on disk, but then when the OS is working on it, OS has to load it into memory, and when you make changes, you need to flush the changes back to the disk, but then that takes time. And oftentimes, what happens is if you don't complete that transaction, that is flush all the changes, possibly because of a crash or some corruption, then you have inconsistency. So FSCK is a Unix utility that is used for file system check, FS for file system, CK for check. And it not only checks, but also repairs. Okay, it makes its best effort to fix inconsistencies. Now it can take a long time, but this is usually run when the OS boots up, and then it does FSCK to check consistency for at least the part it needs. And if it detects anything that's inconsistent, then it attempts to repair it. And that's why sometimes if you have a crash or force the OS to shut down without letting it shut down properly, it's actually running FSCK, so it may take a while next time you boot up. Another way is really you just have to rely on some backup. The backup can be just to make a snapshot. So even if you don't recover everything, you at least recover most of your important data. So that is highly recommended. Now, so one way to make it more robust, make a file system more robust is this thing called log structure file system. Another name for it is called journaling file system. What does that mean? So journaling you can think of as you record, right? A journal, right? Somebody goes on a trip or they write a journal. So every event, they write it down. And so a journal is a lot like a log. And so what that means is this kind of file system, it doesn't just do things. It actually keeps a log, a journal as well. So for everything before it does the update, it actually writes to the journal first. And journal, of course, is on disk. And it records the metadata update as a transaction. So what's a transaction? Transaction means it's all or nothing, right? So you first say, this is the kind of thing I want to do. And so if you don't complete everything, get to the commit point, you actually roll back to before, right? And so it requires something called a commit. A commit is what makes it really effective. Otherwise, it's all staging. A lot like when you use your, Git or any type of a version control system, right? So there is a commit concept. So before you commit, you have to stage it. And so that is, here's the things I want to do. And so it writes to this log or this journal. And then it does one at a time. And when it finishes everything, that's when the commit happens. That says, yes, that's effective. Then, so all of them take effect. Otherwise, it's still in staging area, so you still have a chance to undo it. Because if you only do part of the way, not the whole way, then it's inconsistent, right? So, for consistency is more important. So you roll back as if that never happened, right? As those writes never happened. And you can do that because of this journaling mechanism, right? So that means it is that tentative stage when you are carrying out the updates, but you haven't done it in a consistent way. So it is possible the next time the OS does a check, say, oh, this looks inconsistent, but because of the journal, you're allowed to roll back. So you may have lost some changes, but that's at least it's consistent. Okay. So or another way would be, well, you roll it enough, and then part of the updates that's all known. You just have to actually commit, right? So, or the remaining part of things, if there's enough information for there to be performed, then it would just take it to completion and then do the commit. So it's not like you always lose something, you always roll back. No, it depends on if you have enough information there to allow you to finish that transaction. So that's the so what are the advantages? Well, that you have a lot more you can work with as an OS or as a file system to bring your file system to a consistent state. So it's much faster recovery. In fact, more information, so you have a better chance to recover correctly. Especially from a crash or forced shutdown, and it removes the chances of the inconsistent metadata. Right? So sometimes you make a change and it says, oh, well, the file length hasn't been updated, but all the other parts have been updated, so you can actually make them consistent based on what it has logged. So the last part is a case study, and this is the waffle of file system. And this is an example of more of a network appliance type of file system, in that it's designed for these distributed appliances. So appliances on the network, and they would still need to make access to files over a number of network protocols. So it can work with NFS. So we'll talk about this in the next chapter. NFS is a network file system invented by Sun Microsystems. CIFS, that's more Windows, or you can do like HTTP, FTP. So these can also be protocols to access file systems. And what these do is they assume you have random I/O, or it's particularly optimized for random I/O, and it's random. So it supports this concept of snapshots. So what does that mean? So a snapshot is, you can think of it as an inode that points to a particular version of your file. And if you make random access, chances are you're making copies to just some blocks, maybe not the whole thing. Okay, and so what you do is when you make make changes, what happens is it makes a new snapshot. What does it do? So it creates a new inode. It doesn't throw away, it doesn't override the old inode. Remember what an inode is? Inode is this kind of hybrid, progressively growing type of indexing block allocation scheme, right? Remember? So index is this table where it points to, so block 0 points to this block 1 points, so it's a table, right, of these block pointers. And inode is Unix way, just a quick review. Initially, direct pointers. You have 12 entries. If you have 4K blocks and you have up to 48K of file, you can do just a direct one. And if it's bigger than that, then what does it do? There's a secondary, it has a pointer to a page or a block of these pointers, right? So secondary index. And then that allows you to have another, say, 1K entries, right? So, and then if that's not enough, then you do a additional level of indirections. It progressively grows. And so that's what an inode is. So here, instead of writing in place, what it does is creates just a new inode. And so the parts, it doesn't have to change, it just has to include a pointer, right, to those same blocks. So the parts it changes, what happens, it doesn't write over the old one, at least not right away anyway. Instead, it creates it allocates a new block and then points to that new block, right? So that way, the blocks that haven't changed, the new inode still points to the old ones. But the ones that change, well, it points to the new one. So here is just a number of pictures to show this. So initially, before a snapshot, so you have inode, block A, B, C, D, E, and then after a snapshot, and before you make any change, so what it does is it allocates a new snapshot, tentatively put the same pointer, so that's almost like a copy of these references, right? So to these blocks. And if it says, okay, well, D, the block D here should be changed then what happens? Well, the old block D is still pointed to by the old one. And the new one is created, and so the new snapshot points to the new D instead of the old D. Okay, so that way it's almost like versioning. So you have a new version of your file, but does it take up double the space? No, it actually reuses as much of the same space as before. Okay, so that way it is good for several reasons. You can imagine for flash memory, this is desirable, right? Because for flash memory, first you can't really, or you don't really want to keep overriding the same, or you don't want to do update in place. In other words, overwrite. Why? Because that requires you to you erase a lot of other blocks, right? Just to make changes to a small one. And so this way, it basically says, I keep that around, but mark it as reclaimable. Later, I'll consolidate these or erase them in a batch. That saves me some work, right? And then another is for versioning. So that way, in a way, you kind of have that log, right? So you can say, oh, for a few minutes ago, this is a snapshot. A few other minutes ago, that's another snapshot. So if you really want to trace back and say, oh, no, I shouldn't have saved over, yes, you have a chance to recover your previous version. That's nice. And also, what's another nice thing about this? Well, it's basically automatic for copy on write, right? So that means if you just make a copy and you don't make any changes, well, you only need a separate inode. You don't need a storage space for it, right? It points, and anytime you try to make a change, well, it on demand makes a new copy for you to make the change, right? So built-in copy on write, and that's nice, right? So that way it doesn't use more space than you really need to. It saves the work on copying. Okay, so that is all I want to cover for file system implementation. The chapter actually has a little bit more material on this. You can read up on it, but I think these are really the more interesting parts I want to cover. So, yes?
What if you don't have the space to write a new file?
Right, so what happens, okay, you can read the book on the explanation for this is they always keep a watermark, right? Just like remember when we talk about memory, right? There's that free frame list. This is very much like that too, right? So you don't go all the way until you run out of free blocks or free frames. Once it drops below a certain threshold, then yes, it starts freeing up things, okay? And in fact, you can do it in the background as well. Right, so that way, even before you hit the threshold, it says, "Oh, this looks like all of these in the same block, flash block. That is, all these pages in the same flash block are now obsolete." Then yes, you can actually erase them in one batch, as opposed to having to do additional copying. So there's a number of things that OS can do to optimize this, but universally you have that threshold. So once you count the number of free disk blocks or free the basic units of non-volatile storage. And once it drops below a threshold, that watermark, then that's when OS kicks in and it starts freeing things. Okay, so that way you hopefully never run into that situation. But if you're unlucky, it grabs all of the frames, all of the blocks. Sorry, yeah, you just have to wait.
But is Snapshot know like the block was free?
Yes, the OS does have to keep. I remember last time we talked about the free space management. Remember this topic? So there was there's bit vector for contiguous, linked list for linked allocation, grouping that's like index, linked index allocation or counting that's contiguous. Right? Remember? So somebody has to do the bookkeeping for the free blocks. Okay, so yeah, and so it does know how much space it has, and it would do the free. Oh, man, that specific one, as you know, is based on the inode scheme, right? So that's very much like the Berkeley inode scheme. So that is more the linked index, so or a hybrid really. So you have the initial index if the file is small enough. If not enough, that I know contains another link to another index, right? The indirect index. If that's not enough, 2 levels of the indirect index, right? So and 3 level, it can do triple indirect. Okay, so that is chapter 14, and what I'll do is chapter 15 next. And this talks a few things about the file system internals. Used to be part of implementation, but I think they wanted to split out more optional material from the more core stuff. So, but that's okay. We'll talk about a few of these. But again, I'm only picking certain number of topics from here so that if you're interested, you can read more. But these are the parts I think are more interesting. So now, file system is used not just for files or for that interface is used to access other things. And so you have a kind of the real file system versus a virtual file system. What does that mean? Virtual means you read or write a lot like what you do to a file, but in reality it's not a file. Or it doesn't have to be real file, it's just data. And so you use the file interface to access data, okay? And so, for example, Solaris has a number of different things. So the tempfs is one where you have the need to create temporary files. I mean, if you write programs, yeah, that happens a lot. And so where is that tempfs? Well, it may use either RAM for that purpose, or it may use some other type of memory. That's not disk, that's not flash, that's not anything. That really just a way for storing temporary things. And then, so that it does look like a file system you read or write, but then because it's temporary and it goes away, it gets wiped, you might as well just map that directly to memory. So to the user, it really doesn't make any difference, other than the fact that it looks really fast. Okay. Object-fs is an interface into kernel memory to get kernel symbols for debugging. Again, that is accessed through a file I/O type of call, but then you are actually accessing some tables or some structures in kernel. Now, CTFS is a contract file system, or what that is for managing daemons. What are daemons? So daemons are these processes that are started when the OS boots up, right? OS boots up and then it needs to support some services. So maybe you have a daemon for your server, like FTP, HTTP, or some kind of backup job, backup daemon, right? Other things. So these have to be running processes. They don't take up a lot of time. They're not user processes. They're there to perform some tasks for the kernel, right? So there's this kind of contract of file system, not a real file, but then just for the purpose of managing these daemons. There's LOFS, LO for loopback file system, and so this is a way for doing some kind of mapping, so allow one file system to be accessed in place for another. And procfs is kernel interface to process structure as a file system. So again, so a lot of these have to do with almost like shared memory, but then you attempt to open these like files, and in fact you even specify a path. But the path has special interpretation, and the OS takes over and then does the memory mapping as opposed to actually accessing the real file system. There's UFS and ZFS. Those would be the real general purpose file system for real storage. Okay. And so now a file system is organized in this way. So you have, first you partition up your disk, if you do. Otherwise, it's one partition, right? And then each partition would have at the beginning, one directory structure that then it defines how the rest of the partition is used. So once a partition is formatted, it's called a volume. Okay, and so it could be divided this way. So partition A, B, C, D, and then so there could be volume 1 corresponding to partition A, volume 2 corresponding to partition B. But the volume can also be one that encompasses multiple partitions across different devices. Okay, so like here, storage device 2, device 3, these are different devices, but they get lumped together as one volume. That can happen too, depending on if the OS supports that. Okay, and so to do that, it does what's called mounting. What's mounting? Mounting, like I said before, like if you have some storage device that may or may not be connected, right? Then the mounting is a way to say, okay, now I understand this storage device. I want to integrate it into my directory structure or file structure. And so mounting says connect this file system, right, which is associated with one or more devices, mount it into my directory tree, right? So on the top, that's the root. And you have users and then several parts. And then there are other parts where you can specify what's called a mount point. And the mount point is, you can think of it as an empty directory, but then the root of that file system gets stuck in there. And then you can be accessed as part of your directory tree. So that would be an example of, say, a mount point. So even you can even mount it under one of the users. So there's users, Sue, Jane, and then prog, doc, right? So a whole subtree can be mounted, say, here for just the user. So that means different users may have their home directory or their directory structure on entirely different devices. That's possible too, but then they can be accessed uniformly in the same directory tree structure. So partition can be a volume containing file system, or it could be a raw partition, so unformatted, or just really low level and not any structure. So it's raw storage. You use it a lot like just array. Now, you could have a root partition which contains the OS and it can be booted up, or other partitions that can maybe holding whole other OSs, and so booting up time it allows you to choose which OS you want to boot up. Okay, or it could be a raw partition. And the mounting could be done either automatically or manually. So certain things like your USB stick, that would usually not even be known until you plug in, or other network drives could be discovered and mounted as the system runs. And the boot block would contain a bootloader, and so that's code to bootstrap the OS. So that's enough code. It itself is not OS, but it understands enough, including device driver, include any storage access. Maybe if you access network drive, you don't even need a local drive. You just need enough of it so that it implements just enough of the protocol to fetch the code and then jump to it. And that code can be part of the OS, then you bootstrap, right? It does more to set itself up, but it doesn't have everything. Then it fetches from additional disk or additional server or somewhere else. So it keeps loading more, adds to itself to build itself up, right? So that would be bootstrapping. And mounting time, file system consistency is checked. Okay, so that's what I was saying earlier. So I'm booting up, and well, first the bootstrapper bootloader is running. That's not the OS, but then it accesses certain file system for booting for loading the OS image or part of the OS image. But before it does that, it has to do some mounting, and then that's when consistency is checked. Right, and then when it's if it's it has all the metadata correct, you assume it's safe to load. If not, try to fix it. Okay, and it adds it to a mount table and then does a normal access. The virtual file system is what I was talking about a little earlier in the Syllabus example. Some things may look like file access API, but really they're just a way to access the data structure. And so there, how does that work? So instead of inodes, it uses what's called vnodes. So that would be virtual file system V, the virtual nodes. So still, it's a structure that exists, and the kernel still maintains most of it, but then uses that to do the mapping to the shared memory structure, or to do certain I/O operations, right? And but otherwise, you still call them with your open, read, write, and other things. Okay. So here is an illustration taken from the book. So if file system interface may access real file system or the VFS interface. And that has either access to local file system, type 1, type 2, or a remote one that's over network and other things, right? So API is consistent, so that way it separates the implementation dependent issues from the user. So that way the user just treats them just like any other file access. Now in Linux, you can have VFS access to these various objects. So you can open inode as an individual file. You can open the file, of course, right? But inode itself, that you can think of it as metadata, right? You can open that as using a file system interface. Superblock would be entire file system, or dentry. What's dentry? Well, D is directory, so D entry or directory entry. So that is, it's a data structure for keeping track of a particular entry in the directory, right? So it could correspond to either a file or a subdirectory, right? So that's what a D entry is. So that can also be opened in a Linux virtual file system. Okay, so it's not just for opening what you know as files, but these other objects as well. Now, file sharing on distributed systems can be done over some network protocols such as FTP and HTTP, or some there's SOAP protocol, a few others. So these may be either anonymous, so that means doesn't require login, username authentication, or they may be authenticated, right? And it could be done automatically using distributed file system or via web protocol and others. And even web sometimes gives you, like depending on which server, so Apache, one of the most popular ones, allows you to bring up a path, but then it provides its basic access control. So it may have a file, just defines a user password, and then it's a web server that it reinforces this kind of the authentication. And if you do distributed system sharing across network, then one of the most common method is called network file system, or NFS, invented by Sun Microsystems. And I'll talk about that in a little bit. And so remember, initially, if we were just talking about one machine and multiple users on the same machine, you can authenticate and do access control based on user concept, right? And because the OS has control over what it means to be a particular user with a particular ID. But what if you have multiple machines, possibly administered by different people? How are you supposed to even know, I claim to be user 23, and that's really user 23? You can't. That would be difficult, right? So that means the management of user identification, authentication has to be handled by some other service, or else it's very easy to fake being some other user, okay? So in client-server model, well, the clients access to make requests to the server to access file, and so client and user on client identification, that is insecure and complicated. And so you really want to be able to authenticate. If it's authenticated on the server side, that's fine because the server has full control over the user identity. And but then still, somebody can still try to fake it. There are some security holes there. But in any case, once authenticated, most of these file system calls are done over like a remote procedure call or RPC. Now NFS is done well. Initially, they assume, okay, if you claim to be user 23 and I allow access to user 23, I just trust you. In the earlier days, you could do that because it's done in a relatively local network. Right? So maybe in the lab, in the department, and the same system administrators would do the management. And so that's mostly trusted. But as soon as you start letting users bring in their own laptops and their own file system, I can set up whatever. I'm a super user. I can set up any ID I want, right? And as long as the ID matches, who are you to say I'm not that user, right? So of course, that's an obvious security hole. So that's why it needs what's called NIS, or Network Information Service, to do the authentication. So instead of trusting the user, you have to go to a server, a lot like a DNS, right? Domain name server, except this is to authenticate the user, and then that is what allows you to get access. So that's an improvement. Now on Windows, you also have similar issues, and so CIFS, so Common Internet File System, forces you to create a network login and use Active Directory for the distributed naming structure. So if you use Windows on your network, then yes, you actually have to do this extra level. So distributed naming service, so these include DNS, NIS, Active Directory for Windows, right? So these implement basically unified access to information needed for remote computing, remote file access, okay? And the trend is more moving towards a lightweight directory access protocol, or LDAP. And so that's single sign-on for an organization. And so Active Directory is an example of this lightweight or LDAP. Directory Access Protocol. Now, file sharing, you're likely to have more failures. Why? Because, well, even local file system can fail, but due to what? Corruption of directory structure, metadata. But remote file system have even more chances of failing. Why? Because not only can your media fail, but also network can get disconnected. Server itself may fail, right? So you have more modes of failure. And so what happens? Well, so it's becoming more important to track state information. So, but then tracking state information can be tricky. So, a lot of web protocols like HTTP actually are stateless. NFS initially was stateless as well. That means whoever the client is has to track a lot of the state and then resubmit this. But then this is a little easier to recover, but it's less secure because someone who wants to hack this, they can just set arbitrary state. But NFS it has moved on to more stateful type of protocol. And what about consistency semantics? So that means this is talking about when you have multiple users all trying to access the same files. Reading is less of a problem, but a lot of file systems do want to allow simultaneous writes, right? So you get the synchronization problem. So what the Unix file system does is, if you have writes to a file, then any write you make needs to be immediately available to any other users who may be accessing the same file. Okay, and so so how can it actually do it? Well, so part of it is it may have to force sharing of this file pointer, that is where you are, and any read or write, it reflects in the file pointer immediately. But of course, that is a lot more work to keep everybody in sync. There's one file system called AFS Andrew file system from Carnegie Mellon that was done to allow looser semantics. That is, you have you allow multiple people to be not only reading but also writing. Okay, but what if somebody's already writing? Well, you don't see their changes until they close that file. So is that a good idea? Well, it's easier for them to implement this, but then to the user, they might feel it's a little strange. It's easier just because you don't have to do that many synchronizations. And in fact, you make all the changes committed locally to your local file system, local speed. But the problem is you create all these multiple versions. How do you merge them back in? That's a problem. Okay, so they have different semantics, and as a programmer or as a user, you may get a little surprised. So anyway, sharing is always complex, and there's different versions of doing this. And one might be simply that once you open the file, anybody else who tries to open it simply gets locked out. A lot like what you had to do with reader-writers type of problem, right? So there's different ways to do anytime you want to do file sharing. Okay, different semantics. So the book actually has more to cover on this. So NFS, I just want to talk a little bit more about NFS. So it is invented by Sun Microsystems, which has done a lot of the seminal work on these workstations. So just to give you a little history, before, at least when I was a student, that was when Sun Microsystems was just coming out. And before we were all logging in with our terminal, text terminal to a shared machine. They call them mini computers, but really they're refrigerator-sized computers. And time shared, most of them were made by digital equipment. So DEC, like VAC 780 was a very popular one. And quite robust. In Berkeley, people put their own Unix on there, as opposed to running the stock OS, which was VAX VMS. And some microsystem, some of the initial people worked on the Berkeley Unix, and then they started this company. So some Berkeley people, some Stanford people. And what did they want to make? They want to make workstations. So workstation is a machine that's more powerful than a personal computer. And it runs Unix, and it's like a pizza box this big and a big screen. So in those days, it was much higher end than your PC, because PCs were little 16-bit, 32, not even 32-bit, tiny little screen. And the workstations were for real engineers, right? Having to do with like CAD layout and everything, high-end stuff. And they need protection, so they're really robust, right? Some Microsoft was targeting the high-end part. So these are not just not PCs. They were really meant to be like taking this refrigerator-sized computer shrunk down to a pizza box machine and big screen. And so, the year after in my sophomore year in college, that was when the department there started putting in these Sun Microsystem workstation. I was like, wow, this huge screen, 20-inch, never seen anything so big. And then they even had mouse, but 3-button mouse. So which button do you click? Anyway, so they were doing this, but before, people were used to the idea of logging into the same timeshare system and in one place. If you have workstations, they're no longer terminals, right? They're actually their own computers. But you still want to be able to share files. So that's where the need for a network file system comes in. So one of these workstations would boot up. Maybe it has a little local disk, but then it does access the file system. But then is there a central file server? Not necessarily. So what happens is then these different workstations would mount each other's file system. So I have some file system here, and maybe my home is on this machine. I can go to another machine, and it mounts my file system from this other machine. Okay, so they can mount each other's file system. And so that was the initial idea. So this was all done over fast local network. So a little slower than your local disk, but for most of the part, it's okay. So it's for access. When they say remote file, they really mean the local network, but then on a different machine. That's what they mean. Okay. But of course, you can do it over a wide area network, but that's much slower. Okay. And so that was done from initial Sun OS Solaris, and on the Sun workstations. And they use, they already had Ethernet, and that was very, very fast in those days. And of course, if you know a little bit about protocols, right, TCP/IP is more the reliable version. And then if you don't want reliable, you don't want to retransmit or reassemble, then you use UDP. Right? And so that's how what it uses as its transport. Now, the architecture is really interconnected workstations. So these machines, independent file systems, but they can mount each other's file system. So that way, I can log into any machine. I don't care where my host directory or my home directory is. It just does it automatically. Okay, and remote directory is mounted over local file system directory, and so it looks any machine I log in looks exactly the same. Okay, and the mount operation needs the host name of the remote directory, but then that's all done. So you just have to replicate enough of that user information on different machines, but then the file system itself is mounted over the network. Okay, and because all of them are supposed to be managed the same way, there's really not that much of a like a fake user, because most people couldn't afford to use one or buy one. These are really expensive. I mean, compared to PCs in any way, and if you try to plug in your own machine, it would be very obvious, because in those days you didn't have Wi-Fi. It was you have to have a physical port to plug it in, and so it would be hard to bring your own machine and try to hack that. But then later, people started having their own machines that are more and more powerful, running OS. Then that became more of an issue. But initially, that wasn't much of an issue. And heterogeneous environment. So this was designed to allow different brands, not just Sun machines. Because Digital they also made the workstations as well. They were called DeckStation, and then later there was Alpha ones. They didn't just make these big machines. They were also making workstations. So different brands, different processor, different OS. But still, they could use this, so it supports heterogeneous environment. So in fact, I remember when I was at Berkeley, they did have different workstations from different vendors, all mounting each other. That was fine. And then the mechanism for doing this was RPC, remote procedure call, right? And then, so NFS, network file system specification. It does distinguish between services provided by a mount mechanism versus the actual remote file access services. So that's really what I wanted to cover for this chapter. There's more, and you can read more about network file system if you want to, but that I think this is really to the extent I want to cover, because those other ones start to get into their own topic. Okay, so we only have a few minutes left, but just a reminder that you should be spending time on your checkpoints. As you can see, the last couple of weeks I didn't have a whole lot to assign. The materials kind of lighter weight, right? And more for your information purpose than anything else. So you really should be spending time on your checkpoint. So in case you haven't seen, this is you can find from your assignments. So project checkpoint 5 has been posted if you haven't seen it, right? So did we go over checkpoint 4? A little bit, right? And checkpoint 5, if you haven't seen it, so here it is. Click on this, and checkpoint 5 is, oops, oh. Where do I, Table, oh, too many indirections. Anyway, this one here. Okay, so this one, if you get checkpoint 4 working, in fact, checkpoint 4 it shouldn't be that difficult. I think once you get checkpoint 1 working, checkpoint 2 is not that hard, right? You just have to use the timer mechanism as opposed to the call to do. And checkpoint 3 may take a little work because you do have to do a little bit of assembly coding, but not that difficult, right? And once you get past checkpoint 3, 4 actually is taking textbook stuff, implementing and trying out, hey, why is this not fair? Right? There's a funny starvation issue, right? That's a little counterintuitive, but then I think that you can figure out because there's 2 ways of blocking somebody. Right? Okay, anyway, so 4, I think, if you think about it, it's not that hard, but I'd like you to think about it. And 5 is more like, okay, you can do a little bit more. Really, there's a couple minor adjustments, right? One is to do a delay function, and then you have to do a delay unit. So what does delay do? Delay just says, I don't want to do anything, so you don't return to me until after so many time units. So what's a time unit? Well, that's part of what I'd like you to figure out and discuss. And based on the available mechanism, so do something that's practical. There's not a standard answer, okay? And so that's delay. And the other is, remember when your main function, if you just return from main, what happens? Well, it kind of falls off. If you don't do anything special, it just kind of falls off. And then you don't know what it does, right? So, so what can you do? Well, what you can do is you push the return address for the thread exit on the stack for main. That way, when it returns, it's an implicit exit, right? And in fact, C library does that. And then what I'd like you to do for the fun part is really the test parking. Remember that fun parking example? Make sure you write it in Python first, and then that way you can do a special version for this. Okay, but you do have to do some adjustments, nothing difficult. So delay is like this. So for now, we do everything as unsigned char or single byte because that's a native word size. And then now is to read the time. But then, of course, it wraps around. So the delay says how many time units, but the time unit is not the same as a what you call. It's not the same as each timer unit, right? Because you can keep a separate integer count. So every time it wraps around, you increment it, right? So your delay time unit can be much larger. Okay, and but of course it's not an exact delay because there's always time between the timer resolution and the time you call and when the delay becomes effective. So yeah, think about what is acceptable or what's practical as a good unit for time in terms of how many counter units. So there's no right or wrong answer, but I'd like you to do a little bit of thinking and explain, okay? And so try to answer these questions, and then and certain assumptions to make it a little easier. And the robust thread termination, so that's easy. You just push the return address before you start the main thread. And parking lot example, make sure you do this one in Python if you haven't. And then make a version so that it works with this example. But here, right, so you have 15 cars, 5 spots, and instead of 15 cars, 5 spots, you make 5 cars and 2 spots. But you say, hey, but I only have 4 threads. How can I do 5 cars? Well, you just have to delay, right? So that way, you just make your test case so that you can recycle some of these threads. So this is done on purpose, so that later your later card comes in. And all right, so it takes a little thinking, but I don't think it's too difficult. The only possible thing, okay, there's extra credit. So you can write your output to UART in a more or less human readable form. So that's, I mean, again, there's no right or wrong answer, but if you do it, yeah, you get extra credit, and the TA, you can try to explain it to the TA. It doesn't have to print out complete sentences, but yeah, something more or less readable. That's okay. Okay, and of course, last year when some students did it, it's like yes, it works, but in the code, ew, that looks really ugly. But if you can make, depends on how much time you have. Okay, so that's all I have for this week, and next week will be the for the last two chapters, and again, I try to keep it more like information, not very heavyweight, and then we have one more week, and then we can wrap it up the week after, right? So, and I can even do some in-class debugging for people who run into very nasty issues. So, okay, if we have time.